let's look at phase change diagrams real fast. See if we can put this somewhere where it'll be out of the way. Hopefully you saw this in chemistry a little bit. If not, we'll go over it again. Phase change diagrams are largely what they say. It's a diagram about phase change. We've always got temperature on the y-axis, and energy is always on the x-axis. What's happening here is that this is depicting any substance. It can be any substance. This one happens to be water. It can be any substance. And what happens is this depicts the temperature change and the phase change as we gradually add energy to that substance, thermal energy. I happen to know this one is water because this flat line here is at 0 degrees Celsius, which is the freezing point for water. This flat line here is at 100 degrees Celsius, which is the boiling point for water. So I know this diagram happens to be water. If it were a different substance, these 2 points would be different. But there are some phase changes that take place too, and that's what the line indicates. So let's go ahead and look at some of those. First thing we want to do, hopefully you can see this, it says label the phase changes, and there's vaporization, melting, freezing, and condensation. I just want to label those on this diagram. So take a minute, just pause the video real quick and see if you can label where these 4 things need to go. Alright, so we're going to go ahead and put these on here. Hopefully you've thought about this already. Vaporization, we're going to start with that one. Vaporization actually goes right here. And when I write vaporization, you should do this as well. I'm actually going to draw an arrow that goes to the right. We'll talk about why in just a minute. We'll go ahead and stay at number 4 because condensation should also go at number 4. Condensation also goes at number 4. A lot of people think it's at 3 or 5. They kind of get confused. It's actually at the same place as vaporization. And we're going to draw this arrow going to the left. Vaporization and condensation. You know what I'm actually going to do is before I go on any further, I'm going to go to the second question. Should have done this one first. What phases of matter are present at each numbered location? Once we know this, we can understand the phase changes a little bit better. Right? So what phases of matter? At number 1, 2, 3, 4, and 5. And by phases of matter, remember I mean solid, liquid, and gas. Go ahead and pause the video if you want to real quick and see if you can figure that out on your own. Number 1, down there at number 1, solid only. All we have is solid down there. Just the solid phase present. Number 3, liquid only. Let's use a different color. Solid only at number 1, liquid only at number 3, gas only at number 5. Right? Which means, okay, you might have noticed I left out 2 and 4, did that intentionally. And notice that those places look different. Those are the only places on the graph that have a horizontal line. Some special things going on there. Phase changes, like we put right here already. At number 2 is in the process of moving from a solid to a liquid or vice versa. So while that's going on, you have both solid and liquid present at the same time. Likewise, at number 4, we're going from liquid to gas or gas to liquid. So at number 4, we have both liquid and gas present at the same time. So we need to know that. You need to memorize what phase of matter is present at each of these locations. And then you also need to know the phase changes, which we were doing a minute ago. Let's go ahead and finish that. So we know vaporization and condensation are up here in number 4. Vaporization is going to the right for a couple of reasons. Number 1 is because vaporization is going from a liquid to a gas. We're going this direction. Condensation is the opposite direction. Condensation is when a gas is turning back into a liquid. So that's part of the reason for this arrow. But another reason is this. If we look at our states of matter, hopefully you can tell that since gas is over here on the far right side where we have the highest energy, and then liquid, and then solid where we have the lowest energy, what you need to know is that the gas state is the highest energy state. Liquid is lower energy, solid even lower energy than that. So if we're vaporizing something, by the way, vaporization, another word for vaporization is boiling. You need to know that. If we're doing vaporization going from liquid to gas, vaporization is an energy absorbing process. You should write that down. Because to become a gas from a liquid, this substance has to absorb energy. We'll talk more about that in a minute. Whereas if we have condensation going on, gas going to liquid, the substance has to lose energy or release energy to do that phase change. So that's what these arrows are about. Two more phase changes, melting and freezing is what we left out, and you might have guessed that they go here at number 2. Both of them go at number 2. So I'm going to put melting here, I'm going to put freezing here, and I'll let you guess what directions the arrows go. You're right, melting goes to the right, freezing goes to the left. Make sure you write that down. So melting is an energy absorbing process. We have to gain energy to go from a solid to a liquid because a liquid is a higher energy state. Freezing is an energy releasing process. In order to freeze water, energy has to be released because going from liquid to solid, solid is a lower energy state. So that's the first thing we got to understand about here, about a phase change diagram, and just what's on it. Where are the phases of matter? What phases of matter are present at each location? And where are the phase changes? Notice we really only have 2 phase changes, even though there were 4 words here. Melting and freezing is really the same thing, it's just in opposite directions. Solid to liquid or liquid to solid. Same thing with vaporization and condensation. It's really the same thing, it's just in opposite directions. So really only 2 phase changes, just opposite directions. So understand this, make sure you get this written down. Pause the video for just a second if you need to write all this down. Because I'm going to get rid of it. Because we're going to move on with the next questions. First question, how much energy is absorbed by this water during the melting stage? In order to answer questions like this, you have to know what we just talked about, which is where the melting stage is. Hopefully you remember that the melting stage is at number 2. How much energy is absorbed during that stage? What that means is this. At the beginning of this melting phase, which happens right here, we started out with 10 joules of energy. At the end of melting, we have all of this substance completely melted. All of the ice has been melted away and turned into liquid. When that happens at 30 joules of energy. How much energy was absorbed to go from 10 to 30? Well, that's really easy to figure out. All we got to do is subtract, and we get 20 joules of energy that must be absorbed to go from all the way through the melting phase of this substance. What does the next one say? How much energy is absorbed to bring the water from frozen, and it says to start at 10 joules, to the beginning of boiling? Again, you got to know where this stuff is. Let's get rid of this. Frozen, we're going to start from 10 joules. It specifically says to start right here. So we're going to bring it from this frozen state, begin to melt it, and then take it all the way through to the beginning of boiling, which is right here. We're going to say that that's sitting at 90 joules. It may not be exactly, but that's what I'm going to say. How much energy is absorbed during all this to go from 10 to 90? Again, should be easy to figure out because 90 minus 10 gives us a total 80 joules of energy that this thing had to absorb in order to melt all of this ice and bring the liquid all the way up to a temperature where it begins to vaporize. I want you to notice something here. I'm going to pause for a second. We're going to answer the third question in a minute. 1, 3, and 5, those are the only places where the temperature is increasing. 2 and 4, temperature is not increasing. Because here's what's going on this graph. Only one of 2 things is happening at any one time. And that is either a phase change, that's what this is called, or a temperature change. We can't do both at the same time. When energy is added to a substance, only one of those 2 things can change. Either the temperature can change if that's energetically favorable, or if the temperature is just too high, then what's going to start to happen is the phase is going to change because that's energetically favorable at that time. But you can't do both at the same time. That's often counterintuitive. For instance, when you're melting ice, a lot of people think that the temperature of the ice increases as that happens. Well, it actually doesn't. As long as there's solid and liquid available, the temperature stays the same. The temperature stays the same. Same thing with boiling water. It doesn't matter whether you boil water really hard or really soft. If the water's boiling, the temperature is 100 degrees Celsius. Now, it may take longer to get through that, but the temperature stays the same. So at a phase change, temperature does not change. It can't. And when temperature is changing, The phase doesn't change. There's only one phase of matter present at number 3, and that's a liquid. At number 5, it's all gas. Number 1, it's all solid. So there's either phase change or temperature change going on at any time in this graph. Should have mentioned that earlier, but we got it now. Question number 3, it says during the condensation phase, how much energy is released? We got to know where the condensation phase is. It's up here at number 4. At the beginning of condensation, I'm going to say that's at 90. Go all the way through condensation, and we end up at, let's say it's 125 right there. All right, close enough-ish. So we're going to just simply subtract that. 125 minus 90 gives us 35 joules of energy absorbed, released to do condensation, because condensation is this direction. If it was vaporization, it'd be the same amount of energy, but the energy gets absorbed to go the opposite direction. Right? So this is how we need to understand a phase change.